Well, students, in the last class, we have derived an upper bound for the total error involved in the central difference formula for approximating the second derivative of a function f at a point x. From this upper bound, we observe that there is a critical point, say h star, which is obtained as the point at which the upper bound attains its minimum. Now from this, we can see that the total error may tend to decrease as we approach this h star from the right hand side of h star. Whereas if we choose any h which is less than h star, we may tend to get a larger value for the total error. Note that this is just a possibility that we infer from this inequality. In this class, we will show by an example that this can indeed happen in the reality. Let us consider f of x equal to cos x, a very simple function to handle exactly. And we are interested in finding f double dash of pi by 6. Now, instead of using the exact value of the function cos x, we unfortunately used some approximate values of the function at the node points. And we know that we have taken these values with 6 significant digits when compared to the exact value. Okay, that is given to us. From this information, we can estimate the epsilons. That is the key idea here. If you recall, we have a definition for significant digits. As per the definition, we can see that f of xi minus fi, that is exact value minus approximate value divided by exact value, is less than or equal to 0.5 into 10 to the power of minus 5, because we have assumed that we have 6 significant digits. From here, we have to get the estimate for epsilons. Note that f of xi, whatever may be xi, we know that it will be less than or equal to 1, right? So we will use this very rough estimate for f of xi, and from there we can see that f of xi minus fi, if you recall, f of xi is equal to fi plus epsilon I. These epsilons are coming through this expression, and therefore we want an estimate for fi, right? That is what we will be finally taking as epsilon i's, and that is given by 0.5 into 10 to the power of minus 5 in this example. From here, we come to know what is epsilon infinity, right? And assume that other than approximation in the function values, all other parameters are calculated or used exactly. Well, ideally, I should have put an infinite norm here, but I have a purpose for this. And we now know the estimate for this term, right? So I'm just plugging in x1 equal to pi by 6 in the total error, and epsilon infinity, whatever it may, it should be surely less than or equal to 0.5 into 10 to the power of minus 5. Well, why I have not frozen this with infinite norm is because I have a reason. Instead of taking infinite norm, I'm just taking this xi to be pi by 6. Both approximations are okay, but this gives a bit sharper upper bound for you. That is why I have kept this term as it is without freezing it to by putting the infinite norm. Okay. Now I will eliminate this xi by putting xi as pi by 6. You can also use the infinite norm here. There should not be any problem. But this gives more optimal upper bound for your total error. That is why I have chosen like this. Well, so when you use these two parameters, you can see that the right hand side takes the form h square by 12 into cos pi by 6 plus 4 by h square into 0.5 into 10 to the power of minus 5. Now you see this is something looking like h square plus 1 by h square, right? So I'm just putting all the values here and writing it in this form. Now just consider this as a function of h and try to find what is the minimum of this function. So that will be the critical point h star as it comes in this graph, and that h star is the point beyond which if you go to reduce the value of h, your total error will actually keep on increasing. So therefore, finding this critical point h star is very important for you while working with any finite difference formulas on a computer. That is why we are doing this exercise. It's a very important step for us. And that critical point h star is obtained as the minimum of this function, right? Now, how to find the minimum of this function? Well, we know how to find the minimum of this function e of h. And once you find that, then the bound e of h, that is the right-hand side, indicates that there is a small value of h, that is h star, such that the bound increases rapidly as you go on decreasing h beyond that h star. That is, if you go on taking h less than that h star, then you will tend to only increase the total error. Therefore, don't ever try to take a value of h which is less than that critical value. That is the idea of this analysis. Let us see how to find this h star. Well, you can find it by first differentiating e and equating it to 0 and see the root of this nonlinear equation. And in this particular example, it happens to be 0.129. So this is the critical value of your h, beyond which if you try to take the value h, you will tend to only increase the total error. That is the message. So you have roughly the graph of the function e looks like this. This is your 0.129. So if you take h somewhere here, then you are expected to get smaller error. Whereas if you take a h this side, you are expected to get a larger error, right? So that is the idea. Let us try to compute the approximate value of f double dash at pi by 6 using the central difference formula by taking different values of h and see whether our analysis indeed goes through in the numerical computation. Let us note that the exact value of f double dash of pi by 6 is approximately minus 0.866. Let us do the computation. So what we are doing is we are taking different values of h, plugging in the corresponding function values and h value into our central difference formula and finding the value given by that formula on a computer. And then we are comparing that with our exact value. So the difference between f double dash of pi by 6 minus d bar 2h f of pi by 6 is what I'm taking as total error, that is shown here. And whatever h is there, you can just plug in the expression for e of h, that is given like this. And I'm also showing the value of e of h here. Now you see the critical value is 0.129. I have taken h equal to 0.2. Therefore, your h star is somewhere here. I have taken my h here. So you are supposed to have nice total errors when you are staying in this part. Now I'm taking h equal to 0.129. This is exactly the critical point. And the central difference formula gives us this value. The error is 0.0012. You can see that from h equal to 0.2 to h equal to 0.129, the total error has decreased. It means your central difference formula is working well when you went from h equal to 0.2 to h star, right? It worked well. Let us now go further below h star and choose our h this side and see how this central difference formula behaves. I have gone to h is equal to 0.005. And here I got the value from the central difference formula as minus 0.8. You can see from here to here, the total error has increased drastically. Well, if you see, this computation is done in a very recent computer with 64-bit processor. And you can see that this arithmetic error is still playing a very crucial role in amplifying the total error for such a small computation also. Therefore, one cannot ignore such things and do computations, then we may land up in some disasters. That is what all these examples show. I have even gone much far from h star towards 0 and took h equal to 0.001, and the central difference formula simply gave second derivative of f at pi by 6 as 0 up to the decimal digits shown here, and thereby it committed almost 100% error. And if you go on doing this, you will land up in much bigger disasters. Note that we got the critical point h star equal to 0.129 with respect to the approximation that we have chosen. If you recall, we have chosen that the approximation in the function value is up to 6 significant digits. With respect to that, we got this h star. However, the critical point for the computer on which I have done this computation may be different. Let us do another example. Let us take the function f of x is equal to ln of x, where ln is the natural logarithm. And let us consider the central difference formula for approximating f dash of x. If you recall, it is given by d h naught f of x. That is the notation we use generally for the central difference formula, and that is given by f of x plus h minus f of x minus h divided by 2h. Well, this is the central difference formula with node points x naught, which is x minus h, x1, which is x, and x2, which is x plus h. Well, here the formula doesn't depend on x1, but however, it is included in the node points. Similarly, you can also devise central difference formula for f dash that involves 5 points, say x, x minus h this side, and x minus 2h, and similarly that side you have x plus h, x plus 2h, and the formula that comes out of these nodes will also be called the central difference formula for f dash with 5 nodes. That's like that you can develop central difference formula with any given number of nodes of this structure. Like you should have the point x at which you want to find the derivative as the center of all the nodes. So such formulas are generally called the central difference formulas. And here we are considering the central difference formula with 3 nodes, and it is given by this formula. Now, when you substitute f of x equal to log x, this is written as log x plus h minus log x minus h divided by 2h, right? Now, if you recall, we have derived an expression for the mathematical error in the class, and it is given by minus h squared by 6 f double dash of eta, right? Where eta lies between x minus h and x plus h. Now, for the arithmetic error, we will assume that we have committed an error epsilon minus while taking the function value at the node x minus h, and therefore it is given by f of x minus h minus, let's call the corresponding approximate value by f minus, and that is given by log x minus h minus, let us use the floating point approximation notation here, ln of x minus h. Okay, so this is what, for the notation convenience, I'm just denoting it by f minus here. And similarly, epsilon plus is given by f of x plus h minus f plus, and that is nothing but the floating point approximation of the value of log at x plus h. Now, the central difference formula with arithmetic error is given by d dash h0 of f of x, and that is given by f plus minus f minus divided by 2h, right? Therefore, the arithmetic error involved in the central difference formula is given by d h naught f of x minus dh naught dash f of x, right? And that is given by f of x plus h minus f of x minus h divided by 2h, right? Minus f plus minus f minus divided by 2h. And that, if we use the notation epsilon, we get epsilon plus minus epsilon minus divided by 2h, right? Now, that's the expression for the arithmetic error involved in the central difference formula. Let us take modulus on both sides and write mod AE is equal to mod epsilon plus minus epsilon minus divided by 2h, and that is less than or equal to mod epsilon plus mod epsilon minus divided by 2h, right? Now, if we know some more information about this epsilon, say if you assume that the function values are taken with so many significant digits, or the function values are approximated using some n-digit rounding or chopping, in some way or the other, if you know an estimate for these epsilons, then further you can dominate the arithmetic error with that information. Like in the last example, we assumed that the function values are used with 6 significant digits. From there, we got an estimate for the epsilon infinity. Similarly, let us simply take that epsilon plus is less than or equal to 1 by 2 into 10 to the power of minus 2, and epsilon minus is also less than or equal to 1 by 2 into 10 to the power of minus 2. With this, you can write mod AE is less than or equal to 1 by 2h into 10 to the power of minus 2, right? Similarly, we can also get the upper bound for the mathematical error which can be written as h square by 6 mod f double dash of, what is the notation we have used? We have used eta here. So let me just use the same notation, eta, right? Further, if we know that f is C2 in a closed and bounded interval, then we can further write this as less than or equal to h square by 6 into m, where mod f double dash of eta is less than or equal to m for all eta in the interval of our interest. Combining all this, we can estimate the total error as f dash of x minus d not h bar f of x as h square by 6 into m plus 1 by 2h into 10 to the power of minus 2, right? Now, to find the critical value of h, generally we denote it by h star. Let us take E of h is equal to m by 6 into h square plus 1 by 2h into 10 to the power of minus 2, and h star is nothing but the point at which this function attains its minimum. Therefore, let us first find the derivative of the function e of h, which is given by m by 3 times h minus 10 to the power of minus 2 divided by 2h square, right? And now we have to equate this to 0 to get h is equal to the cube root of 3 by 2m into 10 to the power of minus 2. It's better to also check that E attains its minimum at this value of h. How will we check this? Let us denote it by h star. To check that h star is the minimum, what we can do is just find E double dash of h and show that E double dash of h star is strictly greater than 0. So that is not very difficult. You can easily show this. Therefore, the critical value for the total error is therefore given by h star equal to cube root of 3 by 2m into 10 to the power of minus 2. And that is the answer.